Hello everyone, my name is Varat Dau and I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So I welcome you all to this fifth lecture of structure of atom. So up till now, what in the previous classes, what we have seen is we have characterized atom. Uh, Initially, we assumed that atom is a uncuttable part of matter. However, later we discovered with the help of cathode rays and anode rays that atom consists of subatomic particles. The negatively charged particles, subatomic particles, are called as electrons, and their discovery was initiated by discovery of cathode rays. Similarly, the discovery of anode led to the discovery of protons. Then further, we have studied various models of how these electrons and protons are arranged inside the atom. And the various theories which we studied includes the Dalton's theory, the Thomson's theory, and also the Rutherford theory. Further, we have also seen the Rutherford's Wolfville experiments and the experimental observations which he has obtained, and based on that, the theory which he has given. Further, in the last class, what we have seen is we have also seen the wave-like nature, what are waves, their definition, and the electromagnetic spectra. Okay, so now in today's class, what we are going to study is particle nature of electrons, electromagnetic radiation, and Planck's quantum theory. Okay, let me write this down. Lecture 5, structure of atom. Right. The first topic which we are going to study today is particle nature of electromagnetic radiation and Planck's quantum theory. Right. So the electromagnetic wave theory of radiation believed in the continuous generation of energy. This theory explained the phenomenon of propagation of light, such as diffraction and interference, quite successfully, but it failed to explain many phenomena such as black body radiation and photoelectric effect. So what is diffraction? So diffraction is bending of wave around an obstacle, and interference is the combining of two waves of the same frequency to give a wave whose disturbance at each point in space is the algebraic or vector sum of the disturbances provided by each interfering wave at that point. Okay. So let me write this down. The first point is the electromagnetic theory of radiation believed in proposes continuous generation of energy, right? This theory explains the phenomenon of propagation of light such as diffraction and interference. So first discuss what is diffraction. Okay, so diffraction is bending of wave around an obstacle, right? And what is interference? Right? So interferences is the combining of two waves of of the same frequency to give a wave whose disturbance at each point in space is the algebraic or vector sum of the disturbance provided by each interfering wave at that point. Right? So now let us go back. The third point about this theory is that okay, so this theory could not satisfactorily explain the phenomenon of black body radiation and photoelectric effect. Right? So let us study about this first. Black body radiation. So when solids are heated, they emit radiations over a wide range of wavelength, right? Like for example, when an iron bar is heated in a furnace, it emits radiation and becomes dull red, and then progressively becomes more and more red as the temperature increases. When heating is continued, it becomes brighter and brighter. It becomes brighter and then brighter orange and then yellow and then white and finally it becomes blue at very high temperature. As we know, red light has higher wavelength and blue light has lower wavelength. So in terms of wavelength, it means that the radiation emitted goes from a higher wavelength to a lower wavelength, right? Thus, longer wavelengths, that is red color, have a lower intensity and shorter wavelengths have a higher intensity. This means that if this trend were to be continued, the intensity would keep on increasing indefinitely as the wavelength becomes shorter and shorter and may enter ultraviolet region. However, the intensity of black body radiation does not show this expected behavior, right? So an ideal body which emits and absorbs radiations of all wavelengths of frequency is called as black body, and the radiation emitted by this body is called as black body radiation, right? So what is a black body, right? So so let us first define what is a black body. So an ideal black body is that which which emits and absorbs radiations of or wavelengths or frequencies, right? And the radiation emitted by black body, by ideal black body, is called as black body radiation. Thus, the exact distribution of wavelength or frequencies of the emitted radiation from a black body depends upon temperature, right? The third point, the distribution of wavelength emitted by black body depends upon its temperature, right? So at a given temperature, the intensity of radiation emitted from a black body increases with decrease in wavelength. So let me just plot a plot, right? So this is the x-axis, that is the wavelength lambda in, let's say, nanometer, and this is the intensity. So this is the black body radiation, distribution of wavelength of black body radiation at temperature T2, and this is at temperature T1, where T2 is greater than T1 distribution. So this figure is distribution or emission of radiation from a black body at different temperatures, right? So as you can see from here, at any given temperature, let's say this is the given temperature T2, right? So at a given temperature, the intensity of radiation emitted by black body, so intensity first increases. So as we go from the in this direction, right, the intensity is increasing, and as we are going in this direction, the wavelength is increasing, right? So initially the intensity increases with increase in wavelength, right? Or decrease in this thing, and then starts, right? If you either you can start from here or you can start from here. So let us first start from here. So as you can see, the intensity is increasing with decrease in wavelength. So this is the direction of decrease in wavelength, and this is the direction of increase in intensity, right? So as wavelength is decreasing, the intensity is increasing. It is increasing, reaching a maximum value, and then what is happening? Further decrease in wavelength is decreasing the intensity, right? So in this direction, as we are going in this direction, the intensity is decreasing with decreasing wavelength, right? These results, this is the nature of this, like this, and as we decrease the temperature, the curve shifts downwards, right? The curve shifts downwards. So these results could not be explained by the classical wave theory of light. According to this classical wave theory, energy is emitted or absorbed continuously. Therefore, the energy of any electromagnetic radiation is proportional to its intensity and independent of its frequency or wavelength. Thus, the radiation emitted by the body being heated should have the same color same color, that is the same wavelength of frequency throughout, although the intensity of the color might change with variation in temperature, right? Let me write this down. So what we have from this figure, at a given temperature, intensity of radiation emitted from a black body increases with decrease of wavelength, right? It reaches a maximum value at a given wavelength, and then starts to starts decreasing with further decrease of wavelength as shown in figure, right? This can be concluded. Now these results could not be explained by explained. These results could not be explained by the classical wave theory of light, right? Right? So according to classical wave theory, energy is emitted or absorbed continuously, right? Hence, the energy of any electromagnetic radiation is proportional to its intensity and independent of its wavelength or frequency, right? Thus, an ideal black body is also defined as a perfect absorber and a perfect emitter of radiation. This means that the black body absorbs all the radiation falling on it. When such a body is heated, it emits radiations of all wavelength and frequency, and it has been shown that no other body can emit radiant energy more than a black body. Hence, a black body, which is the most efficient absorber of radiant energy, is also the most perfect emitter. A good approximation to a black body is a hollow sphere blackened on the inside and with a small opening, right? So any radiation that enters to the small hole is reflected repeatedly from the walls and reabsorbed inside the sphere until all of the energies eventually becomes absorbed, right? Absorbed, right? What we have is, right? So let us write this down. Thus, an ideal black body is also defined as a perfect absorber and a perfect emitter of radiations. This means that a black body absorbs all radiations falling on it. Okay. When such a body is heated, it emits radiation of all wavelength or frequency, right? Hence, or a black body which is black body is not only a perfect absorber of energy, but is also perfect emitter, right? So now let us study about the photoelectric effect. The second effect, which could not be explained by the classical theory of light, wave theory of light, right? So photoelectric effect, right? So in 1887, Hertz performed very interesting experiments. He observed that when light of certain frequency strikes the surface of some metal, electrons or electric currents are electrons are ejected from the metal, thereby causing and inducing an electric current. The phenomenon of ejection of electrons from the surface of a metal when light of suitable frequency strikes on it is called photoelectric effect, right? And the emitted electrons are called as photoelectrons, right? So let me write this down. In 1887, Hertz performed very interesting experiments in which he observed that when light of certain frequencies strikes the surface of some metal, electrons are ejected from the metals, right? Now, this phenomenon of ejection of electrons from the surface of metal when light of suitable frequency strikes on it, is called as photoelectric effect, right? And the emitted electrons are called as photoelectrons, right? Let me drag a picture which demonstrates this, right? So this is a apparatus. So this is a apparatus showing photoelectric effect, right? So the cell consists of an evacuated chamber. So this is an evacuated chamber, right? Which consists two electrodes connected to an external circuit, right? So there are two electrodes. So this is connected to an external circuit, right? The metal, so this is the metal surface that exhibits the photoelectric effect is made negative electrode. So this is the negative electrode. When light of sufficiently high energy strikes the metal, so this is the light of certain frequency. When it strikes the metal, the electron are ejected from its surface. So this is the direction of electrons and move towards the positive electron. So this is the positive electrode, right? And form the current flowing through the circuit, right? So it may be noted that only a few metals such as cesium, rubidium or potassium, in which the electrons are loosely held by the nucleus, show this effect when visible light falls upon them. Experimental studies of photoelectric effect under different conditions led to the following important conclusions, right? So now you have studied this. So we will study the conclusions. So conclusions, right? So first conclusion is the electrons are ejected from the metal surface as soon as the beam of light strikes the surface, right? Right. That is, there is no time lag between the striking of light beam and the ejection of electrons from the metal surface. Right. Second conclusion is for each metal, certain minimum frequency of light is needed to eject the electrons. This is known as threshold frequency. Mu naught, right? And it is different for different metals, right? So light of frequency less than threshold frequency, that is mu0, cannot eject the electrons no matter how long it falls on the surface, or how high is its intensity. Right? Different for different metals. Cannot eject. Right? So number 3, the kinetic energy of the ejected electrons is directly proportional to the frequency of the incident radiation and is independent of its intensity, right? So the kinetic energy of the ejected electrons is directly proportional to the frequency of the incident radiation. Right? And independent of its intensity. Right? The last one is the number of electrons ejected per second from the metal surface depends upon the intensity or brightness of the incident radiation, but does not depend upon its frequency, right? The number of electrons ejected per second from the metal surface depends upon the intensity and or brightness of incident radiation, but does not depends upon the frequency. Hmm. The variation of kinetic energy of photoelectrons with frequency of the absorbed protons is being shown, right? So I'm going to draw the figure, right? So this is the so, right? So this is what is frequency of light. Right? And this is kinetic energy of ejected electrons, right? And zero is threshold frequency, right? Next figure is like this. So what is this? This is intensity of light, right? Your frequency is constant. right? And this is kinetic energy of ejected electrons, right? So this is a constant value, right? So both of these figure combined, caption would be variation of kinetic energy variation of kinetic energy of photoelectrons with frequency and intensity, right? It is clear from this figure that for ejection of electrons, the frequency mu of light used must be greater than the threshold frequency, that is mu zero. However, the kinetic energy remains constant with change in intensity, right? So all these observations could not be explained on the basis of classical laws of physics. According to the classical laws of physics, the energy content of the beam of light depends upon the brightness of the light, right? So in other words, number of electrons ejected and the kinetic energy associated with them should depend on the brightness of the light. However, as has been discussed above, though the number of electrons ejected depends upon the brightness of light, the kinetic energy of the electron does not, right? For example, red light of frequency from 4.3 to 4.6 into 10 raised to power 14 seconds of any brightness may shine on potassium surface for hours, but it does not eject photoelectrons. But yellow light of even a very weak brightness ejects photoelectrons. This is because the threshold frequency for potassium is 5 into 10 raised to power 14 seconds, and light of frequency more than mu naught, that is yellow light and not the red light, can cause photoelectric effect, right? So let us now move to Planck's quantum theory of radiation, right? So the next topic is Planck's quantum theory of radiation. So all electromagnetic radiations are forms of energy, right? Our body can feel the heat of sunlight, and that is why we avoid the sunlight during the summer and welcome it during the winter. So what is the relationship between the energy and wavelength or frequency of light emitted, right? So electromagnetic wave theory believed in the continuous generation of radiation energy. That is, the energy may be emitted or absorbed in any value from infinitely small to infinitely large. However, this theory could not explain the experimental results, right? Such as black body radiation and photoelectric effect. At the beginning of the 20th century, Max Planck in 1901 gave a new revolutionary theory known as quantum theory of radiation, right? Right. So let us write down the electromagnetic wave theory believed in continuous generation of radiant energy, right? That is, the energy may be emitted or absorbed in any value from infinitely small to infinitely large. right? However, this theory could not explain the experimental results of black body radiation and photoelectric effect, right? So at the beginning of the 20th century, that is in 1901, Max Planck gave a new revolutionary theory known as quantum theory of radiation, right? 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 So let us understand the correct main features of this theory. So the first main feature is radiant energy is not emitted or absorbed continuously, but discontinuously in the form of small packets of energy called as quanta. Each such quanta is associated with a definite amount of energy. So in case of light, this quantum of energy is often called as photon, right? So radiant energy is not emitted or absorbed continuously, but discontinuously in the form of small packets of energy called quanta, right? And each such quantum of energy each such quantum is associated with a definite amount of energy. Okay. In case of light, the quantum of energy is often called photon, right? So number two is the amount of energy associated with a quantum of radiation is proportional to the frequency of light, right? the amount of energy associated with a quantum of radiation is proportional to the frequency of light. Okay. That is E is directly proportional to mu, or E is equal to h nu, where h is the proportionality constant whose value is 6.626 10 raised to power minus 34 joule second. Right. Third one is the total amount of energy emitted or absorbed by a body will be some whole number multiple of quantum, right? Emitted or absorbed by a body will be some whole number multiple of quantum. That is, it is nothing but n into h nu, or it is equal to n into hc by mu, right? N into hc by lambda. This means that a body can emit or absorb energy equal to h nu or 2h nu, 3h nu, like this. And we cannot have, so what does this tell us? That it can be h nu or 2h nu or 3h nu, but total energy cannot be, let's say, 1.6 h nu or 2.8 h nu, like this, right? Energy of radiation and its frequency. The more the energy, the more energetic are the corresponding photons, the more will be the frequency, right? For example, a photon of violet light will be of more energy than that of red light, because former is of larger in frequency, right? So the concept of energy packets of lights supports the corpuscular character, right? It also explains the distribution of intensity in the radiation from a black body as a function of frequency at the temperature, right? So one note which is to be there is the energy possessed by 1 mole of quanta or photons, that is Avogadro number of quanta, is called as 1 Einstein of energy, right? So the energy possessed by 1 mole of quanta or photons, that is Avogadro number of quanta, is called as 1 Einstein. One Einstein of energy, right? So 1 Einstein of energy is equal to n0 h nu, right? So it should be n0 into h nu or n0 into h by lambda, right? So in this class, what we have seen is, we have seen the uh, two theories, that is black body radiation and photoelectric effects, which contradicts the electromagnetic wave theory of radiation, right? So then in detail, we have studied about the blackbody radiation, the curve of the distribution of wavelength of blackbody radiation, and how the effect was discovered, and what is photoelectric effect. We have also seen the characteristics of photoelectric effect, and then in addition, we have also seen the Planck's quantum theory of radiation, that radiant energy is not emitted or absorbed continuously, but discontinuously in the form of small packets of energy called as quanta, and the amount of energy associated with the quantum of radiation is proportional to the frequency of it. This is what we have seen. So in the future class, that is next class, what we are going to do is we are going to solve some examples on this, and then we are going to study the explanation of photoelectric effect using quantum theory, and then we are going to solve some questions based on photoelectric theory, and then we are going to study the atomic spectra, right? So I thank you all for attending this class, and I hope to see you again in the next class. Okay, thank you. So hello everyone, my name is Varad Dow, and I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur, and I am also a PMRF fellow at the same department. So I welcome you all to this sixth lecture of structure of atom. So in the previous class, we have seen that the light was considered to be a wave-like. The light has a dual nature, that is a wave-like and particle-like. So we have studied about the wave-like particle-like nature with the discovery of electrons and protons. Then we have studied the different models which could describe the distribution of the subatomic particles inside the atom. Then further we have seen what are the waves and their fundamental characteristics and various terminologies like wavelength, frequency, and velocity. Further, we have seen why the particle nature of electromagnetic radiation and Planck's quantum theory was originated, and the drawbacks of wave-like nature. So we have studied about the black body radiation and the photoelectric effect, which could not be explained by the wave-like nature of the electromagnetic radiation. Then further, we have studied about Planck's quantum theory, right? And we have also solved a couple of examples. So in today's class, what we are going to study is so the first class, this class could be divided into two parts. So initially we are going to study about some theory, that is the atomic spectra. We'll study about spectra. We'll study about two different types of spectra, that is emission spectra and absorption spectra, right? And difference between them. And then we will study about the emission spectra of hydrogen atom. And in the second part of the lecture, we are going to solve some examples, right? So let us start. So first let me write down. So this is lecture 6, structure of atom, right? So in today's class, we are going to study about atomic spectra. So the first one would be emission spectra, and the other would be absorption spectra, right? So when white light from sun is passed through a prism, it splits into a series of colors known as rainbow of colors, that is violet, indigo, blue, green, yellow, and red. A similar spectrum is observed when a rainbow forms in the sky. This means that sunlight is composed of collection of electromagnetic waves having different wavelengths. The prism bends the light of different wavelengths to different extent. The red color with the longest wavelength is deviated the least, while the violet color with the shortest wavelength is deviated the most. The splitting of light into a series of color bands is known as dispersion, and the series of color bands is called as a spectrum, right? So what we have is the splitting of light into a series of color bands is known as dispersion, right? And the series of color bands is called as spectrum. So in this spectrum, there is a continuity of color, that is one color merges into the other without any gap or discontinuity, and such a spectrum is known as a continuous spectrum, right? The continuous spectrum can also be obtained from the light emitted from some incandescent substance, right? So let us study about atomic spectra. So unlike the spectrum obtained by analyzing the sunlight, the spectra of atoms are not continuous, right? So this is to be noted. So this is point one. So unlike the spectrum of atom are not continuous, right? The spectra of atoms consist of sharp, well-defined lines or bands corresponding to definite frequency, right? The spectra of atom consist of sharp, well-defined lines or bands corresponding to definite frequencies, right? So there are two types of atomic spectra. So first is emission spectra and the other is absorption spectra. Okay, so let us study first about the emission spectra. So the emission spectra are obtained when the radiations emitted from substances that have absorbed that have absorbed energy either by passing electric discharge through a gas at low pressure or by heating the substance to high temperature are analyzed with the help of spectroscope. So atoms, molecules or ions that have absorbed radiations are said to be excited. For example, when the gases or vapors of chemical substance are heated by electric spark, the light is emitted. The color of light depends upon the substance under investigation. Like, for example, sodium or salt of potassium, sodium or salts of potassium, sodium or salts of sodium gives off yellow light, while potassium or salts of potassium produces a violet color. When the radiations emitted by different substances are analyzed, the spectrum obtained consists of a sharp, well-defined lines, each corresponding to a definite frequency of wavelength. When the radiations emitted by different substances are analyzed, the spectrum obtained consists of sharp, well-defined lines, each corresponding to a definite frequency of wavelength. Such a spectrum consists of lines of definite frequency is called as line spectrum or discontinuous spectrum. Okay? So such spectrum are called as continuous spectrum, right? The line spectrum is known as atomic spectra because it is obtained by analyzing the emitted radiations from atoms by application of heat or any other form of energy. By the application of heat or any other form of energy. Right? The pattern of lines in the spectrum of an element is characteristics of that element and is different from all those of other elements, right? Of that element and is different from those of all other elements. Right? So in other words, each element gives a unique spectrum of irrespective of even the form in which it is present. Since atoms of different element give characteristic set of lines of definite frequency of definite frequencies, emission spectra can be used in chemical analysis to identify and estimate the elements present in a sample. Characteristic set of lines to identify and estimate the elements present in a sample. Right? So now let us solve some examples. Let us solve some examples, right? So the first question is, we have electromagnetic radiation of wavelength 242 nanometer is just sufficient to ionize the sodium atom. Right? So calculate the ionization energy of sodium in kilojoule per mole, right? So what we are given is value of Planck's constant has been given to us. So energy possessed by, right, ionization energy. So what we have is E is equals to h nu, which is nothing but hc by lambda, right? Where h has been given to us as 6.626 10 raised to power joule second, right? Thus we are also given hc is 3 into 10 raised to power 8 meter per second, and we are also given lambda is 242 nanometers, which is nothing but this, right? So energy will be hc by lambda, which is multiplied by 3 10 raised to power 8 meter per second divided by 242 into 10 raised to power minus 9 meter, right? So E comes out to be 8.21 10 raised to power minus 19 joule, right? So ionization energy per mole is equals to 8.21 10 raised to power minus 19 joule multiplied by the Avogadro number, right? Which comes out to be 494 into 10 raised to power 3 joules, which is nothing but 494 kilojoule per mole, right? So this is the answer. So the next question which we have is question 2, which is calculate the minimum amount of energy that the photons must possess to eject electrons, cesium metal, right? So what we are given is the threshold frequency of cesium metals is 4.6 10 raised to power 14 second inverse, and H has also been given 6.626 10 raised to power minus joule second, right? So what we want to have to find is the threshold frequency of cesium metal, right? So the threshold frequency, which is mu 0, is the minimum frequency that the photons must possess to eject electrons from metals, right? Therefore the energy corresponding to mu 0 is the minimum energy required, which is also called as work function, right? So, threshold frequency one point six into 10 raised to power 14 second inverse. So the minimum minimum energy required to eject the electrons from cesium metal is given by E0 is nothing but H nu 0, where H is the Planck's constant, right? Which has a unit of joule second multiplied by 4.6 10 raised to power 14 second inverse, which is nothing but 6.63 into 4.6 into 10 raised to power minus 20 joules, which comes out to be 3.05 10 raised to power minus 19 joule. But E0. So the work function is 3.05 into 10 raised to power minus 19 joule, right? So let us move on to the next question. Question 3. Calculate the kinetic energy of the ejected electrons when ultraviolet radiation of frequency 1.6 10 raised to power 15 second inverse strikes the surface of potassium metal, right? So what we are given is, we are given the short frequency of potassium is 5 into 10 raised to power 14 second inverse, and we are also given h is equals to 6.626 10 raised to power minus 34 joule second. Solution, right? Kinetic energy of the ejected electrons is given by total amount of incident energy minus the minimum work function, right? Right? Here mu. So what we are given is, we are given that h is equals to 6.626 10 raised to power minus 34 joule second, plus we are also given the frequency of incident radiation, that is mu, is nothing but 1.6 10 raised to power 50 second inverse. We are also given that mu 0, that is the minimum work function energy, is frequency is 10 raised to power minus 4 second inverse, right? So we just plug the known values into the expression. So what we get is 6.62 10 raised to power minus 34 joule second multiplied by 1.6 10 raised to power 15 minus 5 into 10 raised to power 40 second inverse, which corresponds to 6.68 10 raised to power minus 14 multiplied by given 10 raised to power 14, right, which corresponds to 7.2 10 raised to power minus 19 joule. The required kinetic energy is 7.29 into 10 raised to power minus 19. So let us move on to the fourth question. A 25 watt bulb emits monochromatic yellow light of wavelength 0.47 micrometer. Calculate the rate of emission of quality per second. Right? The solution. We know that energy of one photon is given by E is equals to h cube, which is nothing but E is equal to hc by lambda, where h is the Planck's constant, c is the speed of light, lambda we are already given 0.57 micrometer, right? So E is going to be hc by lambda 6.626 10 raised to power minus 34 joule second multiplied by 3 into 10 raised to power 8 meter per second, right, divided by the wavelength, right? This implies E is nothing but 3.487 10 raised to power minus 19 joule, right? So now what we have is 25 watt is nothing but 25 joule per second. Therefore, number of photons emitted per second is going to be 25 by 3.487 10 raised to power minus 19, which is 7.17 10 raised to power 19 second inverse, right? So this is the answer which you want, right? The next question is question number 5. when light of wavelength 470 nanometer falls on the surface of potassium metal. Electrons are emitted with a velocity of 6.4 10 raised to power 4 meter per second. What is the minimum energy required? To remove an electron from potassium metal. So what we have is velocity of emitted electrons is given to us as 6.4 10 raised to power 4 meter per second, right? And kinetic energy of emitted electrons is half mv square, which is of 9.1. Right? Of 9.1. Sorry. So kinetic energy is half into mass, which is 9.1 10 raised to power minus 31 kg multiplied by the velocity square. Right? So what is the velocity? 6.4 into 10 raised to power 4 meter per second square, right? Which corresponds to kinetic energy as 1.864 10 raised to power minus 31 kg meter square per second square, right? Which corresponds to 1.864 10 raised to power minus 31 joules, right? So energy of photon. So how can you write energy of photon, right? So how we write energy of photon? It is nothing but E is equals to h nu, which is hc by lambda. So E is equals to 6.63 into 10 raised to power minus 34 multiplied by 3 multiplied by 10 raised to power 8 divided by wavelength, which is this. Hence energy of one photon comes out to be 4.23 10 raised to power minus 19 joules, right? Right? So now what we need is the minimum energy required, right? So what we need is minimum energy required to remove an electron is nothing but work function, which is h into nu, right? So now clearly kinetic energy is h nu minus h nu naught, which is h nu minus nu naught, right? Or when you replace this, rearrange it, what we get is h nu naught is equals to h nu minus kinetic energy, right? So which is h nu, which is what, 4.23 10 raised to power minus 19, right? Minus 1.864 into 10 raised to power minus 21, which corresponds to be 421.14 into 10 raised to power minus 21 joule. Minimum energy required per mole is nothing but 421.14 multiplied by 10 raised to power minus 21 multiplied by the Avogadro number, right? Which amounts to this, which is nothing but 253.6 10 raised to power 3 joule per mole, right? So this is the final answer. So I thank you all for attending this class and I hope to see you. Thank you. Hi everyone. So I welcome you all to the 7th lecture of the structure of atom. So myself, I am a Varad Dow, a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So in the previous classes, what we have seen is we have seen about the classical and classical wave theory and particle theory for electromagnetic radiation. We studied that the classical wave theory could not explain photoelectric effect and black body radiation emitted by the electromagnetic radiation, and hence we concluded that light or electromagnetic radiations are not only particle but also they are not only wave-like, they don't have only wave-like behavior but also particle-like behavior, which could be explained, which can explain the photoelectric effect and black body radiation. Further, we learned about the Planck's quantum theory of radiation, and then we also solved some couple of examples based on this, and then we also studied about the atomic spectra, and of atomic spectra we studied about the emission spectra, right? So let me recap, right? So let us start. This is lecture 7, structure of atom. What we are going to study today is atomic spectra. So we studied about what is atomic spectra. So there are two parts of it. One is emission spectra and the other is absorption spectra. Right? So we already studied about the emission spectra, but just to recap, I will say that emission spectra are obtained when the radiations emitted from substance that have absorbed energy either by passing electric discharge through a gas at low pressure or by heating the substance to a high temperature are analyzed with the help of spectroscope, right? The atoms, molecules or ions that have absorbed radiation are said to be excited, right? Right? For example, when the gases or vapor of chemical substances are heated by electric spark, a light is emitted, and the color of light depends upon the substance under investigation. So such a spectrum of line, right? The emission spectra obtained by analyzing radiations emitted by passing electric discharge through hydrogen gas at low temperature, right? Is for this. So the emission spectra is like this. Right? What we have in here is these are the tubes, right? This is the electric circuit. These are now the slits from where the light is going to pass. Right? So this is the direction of light. So this is the direction of light, right? It is going to pass through the slit. Right? So this is it's a different color. So this is a slit, right? And this is the discharge tube containing hydrogen, right? So when this passes through prism, right? This is the prism. So when light through this passes through this prism, it splits, into various components, right? This goes to a screen, right? So this is the screen which we have, right? This is the screen and this is the prism, right? So the spectrum which we obtained is called as electromagnetic spectra, is called as emission spectra, and the nature of this emission spectra is like this, wherein we have these lines, right? So what is this? This is going to be red light. Let's say for example, for hydrogen atom, for hydrogen gas, that's going to be violet, right? And this is called as emission light spectra, or only light spectra, light spectrum. And this whole setup is called as the emission spectrum of hydrogen atom, right? So now let us study about the second type of spectrum. It is called as absorption spectrum, right? So this one, first one was the emission spectrum. Now is the light spectrum. Oh, sorry, the absorption spectrum. So when a continuous electromagnetic radiation, let's say it to be a white light, is allowed to pass through a gas or a solution of some salt and transmitted light is analyzed, we obtain a spectrum in which dark lines are observed in an otherwise continuous spectrum, right? So these dark lines indicate that the radiations of corresponding wavelengths have been absorbed by the substances, right? So such a spectrum containing a few dark lines due to the absorption of light is known as absorption spectrum. So to understand it, let me draw a diagram. What we have is a slit like this. This is going to be a slit, right? This is a slit. This is going to be a light, sunlight, right? It is going to pass through the a beaker containing NaCl solution, right? Let's say it's like this. This is NaCl solution. This is right, and these are the slits, right? Right. Now light passes through this, right? Then it passes through the prism, right? Just like in emission spectrum, right? Then this light splits, right? And then it passes through the screen, right? So this is the screen. So this is the screen which we have, and this is the prism, right? So the spectrum which we obtain in this setting is called as absorption spectrum, and it has these dark lines in it, right? Like this, right? Dark lines. This is called as, right? So this whole full assembly is known as absorption spectrum of sodium chloride, right? So what we have is spectrum containing a few dark lines due to absorption of light is known as absorption spectrum, right? The dark lines, let me write it as number 1. Number 2, characteristics of this spectrum. The dark lines are of definite wavelength and are also characteristics of the substance. Right? It may be noted that these dark lines. So when we say dark lines, I am meaning these dark lines, right? So so these dark lines, right? So these are the characteristics of substances. Right? These dark lines appear exactly at the same place where the lines of emission spectra appear. Right? Lines in right? Lines of emission spectrum appear, right? For example, the emission spectrum of sodium consists of two important yellow lines at 589 nanometer and 589.6 nanometer, right? On the other hand, when white light is passed through, white light is passed through vapor of sodium, we get dark lines in the absorption spectrum at the same place, right? That is at 589 nanometer and 589.6 nanometer. Right? The study of emission or absorption spectra is called as spectroscopy, and this has become very important and essential field for all chemists. It helps to study the electronic structure, right? These characteristic lines in atomic spectrum can also be used in chemical analysis to identify the elements, right? So the study of emission or absorption spectrum is called spectroscopy. right? So why is there this or? This is because both of these methods are contemporary to each other. It is not important to study both of these things, both the emission spectra and the absorption spectra. We don't need to study both of them. We can study either one of them because both of them give us the same information, right? So now let us understand the difference between emission and absorption spectra. Emission and absorption spectra. The difference is here we are going to write emission spectra and here we are going to write about the first point is emission spectrum is obtained when radiations emitted by the excited substance are analyzed with the help of spectroscope, right? Whereas absorption spectrum is obtained when the white light is first passed through the substance in gaseous state or in solution and the transmitted light is analyzed with the help of spectroscopy, right? Emission spectrum is obtained when radiations emitted by the excited substance are analyzed with a spectroscope. Absorption spectrum is obtained when the white light is passed to the substance either in gaseous phase or in solution, right? And the transmitted light is analyzed spectroscope. Second point is emission spectrum consists of emission spectrum. Emission spectrum consists of bright colored lines separated by dark lines, whereas absorption spectrum consists of dark lines in an otherwise continuous spectrum. So emission spectrum consists of bright colored lines separated by dark spaces, whereas absorption spectrum consists of dark lines in an otherwise continuous spectrum, right? So now the next topic which we are going to study is emission spectrum of hydrogen atom. The spectrum of hydrogen atom has played a very important role in the development of atomic structure. The spectrum of hydrogen atom can be obtained by passing an electric discharge through the gas taken in the discharge tube under low pressure. The emitted light is analyzed with the help of spectroscope. Hence, why is that? Because we are using the emission spectrum, right? The spectrum consists of large number of lines appearing in different region of wavelengths. Some of the lines are present in the visible region, while the other are present in violet or infrared region, right? Right. The emission spectrum of hydrogen consists of a large number of lines appearing in different regions of wavelength. So some of these lines are present in the visible region, while the while others in the ultraviolet and infrared region, right? Okay. So the equation which was developed was, so let me write. So in 1885, J.J. Balmer developed a simple relationship among the different wavelengths of the different wavelengths of the series of visible lines in the hydrogen spectrum, right? So this expression is very important. So the expression is 1 by lambda, which is nothing but wave number, which is mu bar in centimeter inverse, is nothing but 109677 into 1 by 2 square minus 1 by n square, right? Where n is an integer equal to or greater than 3, right? That is n can take value 3, 4, 5, etc. And this expression is known as Balmer formula. Right? However, the main limitation of this expression is that it gives lines only in the visible spectrum, right? The Balmer formula gives only the spectral lines in the visible region, right? And these series of lines which appear in the visible region are named as Balmer lines, right? These lines or these series of lines which appear in visible region were named Balmer lines. Soon afterwards, a series of spectral lines of hydrogen atom in different regions were discovered. These lines in different regions were grouped into 5 different series of lines, right? And each line being named after the name of its discoveries, right? So these lines are, let me write it down, different lines or spectral lines for hydrogen atom. So these series of lines which I am writing, right? Spectral lines. So number 1 is, so here I am going to write which series it is. Then here we are going to write region, whether it's in ultraviolet region, infrared region, or visible region. Then and here we are going to write something called as N1 and N2, but we'll look at it afterwards. So first is the Lyman line, and this belongs to ultraviolet region. Second is Balmer line, and it is a visible region. The third is Austen line in infrared region. Bracket lines, these are also in infrared region. And then fund lines. So this is spelled as PFUND. These are also in infrared region, right? And the expression, like similar to this Balmer formula, for all other there is a generalized expression for all of this, and that generalized expression is 1 by lambda is equals to in, so this is wave number, which is nothing but r into 1 by n1 square minus 1 by n2 square, where r is nothing but constant and its value is 109677 centimeter inverse, and n1 n2 are the integers where n2 varies as n1 plus 1, n1, n1 plus 2, n1 plus 3, so on and so forth. And to get the Lyman series line, we have an n1 value of 1 for this, n2 value could be like has been mentioned here, right? Like has been, if n1 is 1, n2 can be 2, 3, 4, 5 as per this expression here, right? Right, this has to be 2, then this can be 4, 5, like this. This is 3, this is 4, 5, 6, right? This is 4, so this could be 5, 6, 7, right? This is 5, then this 6, 7, right? Like this. And but this is valid only for hydrogen atom, right? So a slight correction in this formula could lead us to hydrogen like atoms, right? Right, so let us first write this down. So it may be noted that the above equation is true only for spectral lines of hydrogen atom or hydrogen like atoms, right? So hydrogen, right? So this is the expression only for the different series for hydrogen atom, right? Not this one, this one only for hydrogen atom, right? So if we add one more, that is if we add in here one more term, then what we can have is we can have a so let me just write it down. For hydrogen like atoms, hydrogen like ions, right? For example, right, like this At plus or Li plus 2, the above expression changes. Expression changes as, right? In that case, 1 by lambda is going to be mu bar, which is wave number, which is r into 1 by n1 square minus 1 by n2 square. So here just we are going to add a z square, where z is what? Nuclear charge. For helium plus, z is going to be 2. For Li plus 2, z is going to be 3, and so on, right? So this is the general encompassing equation. If you want for hydrogen, we just put z is equal to 1, and if you want, let's say a Lyman series, we put n1 is equal to 1 and n2 could be 2, 3, 4, 5 up to infinity with numbers, right? So based on this, let us solve an example, right? So the first question which we are going to solve is, what is the wavelength of light emitted when the electron in the hydrogen atom undergoes transition from an energy level with n is equal to 4 to an energy level with n is equal to 2, right? And this is the first part. The second part is, what is the color of the radiation? What we have is, according to, so we are going to solve it based on for hydrogen atom, right? So according to equation, what we have is 1 by lambda is mu bar in centimeter inverse is nothing but r into 1 by n1 square minus 1 by n2 square. So what we are given is, we are already given n1 is equal to 2, n2 is equal to 4, and r is equal to 1096,777 is centimeter inverse, which means 1 by lambda is nothing but, we just put in the values, known values, to get this expression. right? 1 by 2 square minus 1 by 4 square in centimeter inverse. This corresponds to 1 by 4 minus 1 by 60. And when you simplify it, we get it as 4.86 10 raised to the power minus 5 centimeter, which corresponds to about 486 nanometer, right? Sorry. So this is not this. This means lambda is, so this implies lambda is nothing but this, right? So this is one of the value. And since what we are doing, we are dealing with hydrogen atom, and we know N1 is nothing but N2, right? So from this table, what we see is when N1 is equal to 2, we are in the Balmer series and the region is visible, right? So we are in the visible region, and in order to, so we are in the visible region. Region is visible region, and invisible region. If you want to find out whether it's towards red or towards violet, then we will have to look at the electromagnetic spectrum. And when you do that, we see that this is bluish green color, right? So this has also has to be marked, right? So the next question, question 2, right? Right. So what we have is equation, spectral line corresponds to N1 is equal to 3 and N2 is equal to 5. So what we are asked is calculate the wavelength and frequency of this radiation or of this spectral light. So we already know that 1 by lambda is nothing but R into 1 by N1 square minus 1 by N2 square. Here we are given N1 is equal to 3, N2 is equal to 5, and we already know the value of R, which is 109677 centimeter inverse. We plug in the values, what we get is 1 by 3 square minus 1 by 5 square. So when you do the calculation, it turns out to be 1282 10 raised to power minus 5 centimeter, which is nothing but when you convert it into nanometers, right? This corresponds to 1282 10 raised to power minus 7 meter, and okay, this is 12.82, right? 1282 into 10 raised to power minus 9 meter, which is nothing but 122 nanometer, right? And then we also know that lambda into frequency is nothing but speed of light. This implies frequency is c by lambda, which is 3 into 10 raised to power 8 meter per second divided by 1282 10 raised to power minus 9. Hence we get frequency as 2.64 to 10 raised to power 14 second inverse, right? So now moving on to the third question. This is a very important question, right? What we have is what transition in the hydrogen spectrum would have the same wavelength as the Balmer transition, right? So we are given 2 n is equal to 2 of He plus spectrum. So for He plus spectrum, what we have is as it's a hydrogen like ion, what the expression which we are going to have is this one into z square, right? So here in the previous, right, this expression is what we are talking about, right? And we already know that for He atom it is given z is nothing but 2, right? So we are going to utilize this. So for hydrogen atom we are given n is equal to 4n. So what we are given is n1 is equal to 2, n2 is equal to 4n, z is equal to 2. So 1 by lambda is r into 1 by 2 square minus 1 by 4 square into 2 square, which corresponds to 1 by lambda is nothing but 3 by 4r. This is expression 1, right? So for hydrogen atom what we can do is we have 1 by lambda is r into 1 by n1 square minus n2 square, right? Now since this is expression 2, so since lambda is same, we are going to equating equation 1 and 2, and hence what we get is 1 by n1 square minus 1 by n2 square is going to be 3 by 4, right? Now we know that this n1 and n2 has to be integer values. So for this we put in the uh, heat and trial, right? So we also know that it's a Balmer series, right? For hydrogen it's going to be Balmer series. That means n1 is going to be 1. This turns out n2 is going to be 2, right? Therefore the transition from n is equal to 2 to n is equal to 1 in H atom will have the same frequency, will have the same wavelength as the transition from n is equal to 4 to n is equal to 2 in He plus, right? So this is our result, right? Right. So the next topic which we are going to study is the drawbacks of the Rutherford's model, right? So I'm just going to give an overview of this. So according to Rutherford model, an atom consists of a heavy charged particles, heavy charged, heavy. Okay. So according to Rutherford's model, an atom consists of a heavy positively charged nucleus surrounded by a negatively charged electrons moving around it in a circular path, right? So this model was analogous to the solar system, where the nucleus may be compared to the sun and the electrons to the planets. The Coulombic force between the nucleus and the electron would be given by this expression, right? Q1, Q2 by R square, where Q1 and Q2 are the charges and R is the distance of separation between the molecules and the electrons, and K is the proportionality constant, right? And this is similar to the gravitational force between two masses with mass m1 and m2, and the force would be in that case g m1 m2 by r square, right? Where g is the gravitational constant and r is the distance of separation between the planet. However, there is an important difference between the solar system and the nuclear model. The electrons have extremely small mass and are negatively charged, whereas planets are massive and neutral, right? The planets involved in well-defined circular path around the sun, right? So this is also true that the planets revolve in well-defined circular path around the sun. However, there arises a difficulty with Rutherford's model, right? So it failed in the light of electromagnetic principle, right? It was shown by Clerk Maxwell that a charged body moving under the influence of attractive forces loses energy continuously in the form of electromagnetic radiations, right? Thus, unlike a planet, the electron is a charged body and thus it should emit radiations while revolving around the nucleus. As a result of this, the electron should lose energy at every turn and move closer and closer to the nucleus following a spiral path. So what basically said is, although that the force acting between the electrons and nucleus is similar in nature to the gravitational force which is acting between the planets, the main problem with the Rutherford model was that it was shown in by Clerk Maxwell, that when we have an electric field and when there are two charges with the opposite spin and they are revolving around each other, then the charges should emit radiation, and hence the energy should be decreasing with each rotation, and hence the positive charge, the negative charge, that is electron, should somehow collide to the nucleus. So the figure would be, let's say this is the positive charge, that is the nucleus, and this is the electrons, right? So this is revolving around the revolving around the nucleus in, let's say, this fashion, right? So this, let us remove it, and let us say that this is the nucleus which we have. This is the nucleus, right? Let's say this is positively charged and there is an electron, right? So it is getting attracted in this force and it's moving along this direction, right? So because the force here is the electromagnetic attraction, what James Clerk Maxwell showed is that when this complete rotation, so it will not be like this, it should be, because energy is being lost by this electron, because it is going to emit radiation, the path will not be a complete circle, and instead it will be like this. It will be moving, let's say like this, and it will be like this. The path should continuously decrease and eventually the electron should lie on the, should collide with the nucleus, collapse on the nucleus, right? So this was not the case, right? This was one of the major drawback, right, of the Rutherford model, right? Then consequently the orbit will become smaller, like I have said, the orbit should become smaller, and consequently the orbit will become smaller and smaller, and finally the electrons would fall onto the nucleus, right? So in other words, the atom should collapse, and the calculation have shown that it takes only about 10 raised to power minus 8 seconds to happen this, right, for an electron to spiral into the nucleus, right? However, this does not happen. Therefore, Rutherford's model cannot explain the stability of atom if the motion of the electron is described on the basis of classical mechanics and electromagnetic theory, right? Hence, Rutherford's model cannot explain, cannot or could not explain the stability of atom. Obviously, we may think that if motion of electrons in orbits lead to a instability of atom, then why not consider electrons as stationary around the nucleus? However, if the electrons were stationary, electrostatic attraction forces between the nucleus and the electrons would pull electrons towards the nucleus to form a model as described by J.J. Thomson, right? Hence, Rutherford's model failed to explain the existence of certain definite lines in hydrogen spectrum, right? So the other drawback was that Rutherford's model failed to explain the existence of certain definite lines in the hydrogen spectrum, right? If the electrons were to lose energy continuously, the atomic spectrum of hydrogen should have been continuous. However, the spectrum of hydrogen has been found to be discontinuous in the form of characteristic lines of definite wavelengths, right? This is the other serious drawback of the Rutherford model, right? Hence, this model does not explain the structure of atom, that is distribution of electrons around the nucleus and this energy, and thus we need a better model, and that model has been given by Bohr, which is what we are going to study in the next class. But before that, let me write this down. Bohr to lose it. The electromagnetic spectrum, sorry, the emission spectrum, the atomic spectrum, hydrogen should have been continuous, right? However, we found that the spectrum of hydrogen is not continuous, right? Hence, now the next step which we are going to study is Bohr's model. Next model is Bohr's model. So let me do the summary. So in this class, what we have seen is, we have seen that atomic spectrum has two types. One is absorption spectrum and the other is emission spectrum. We studied its similarities and differences, and we also concluded that both of these techniques are complementary. That is, we need not study both of the spectrum. Any one spectrum will give us the essential and as the information, right? Then we studied about emission spectrum of hydrogen. Then we studied about 5 different lines, right, which are Balmer region, Balmer lines, or one lines, right? Or should I write this like Lyman lines, Lyman series, Balmer series, Paschen series, Pound series, and Brackett series. Right? Then we studied about the for different lines, for different series of lines, and for hydrogen-like species. Then we solved some example based on this concept, and finally we studied about the drawbacks of the Rutherford model, which are that it could not explain the stability of atom, right? And hence there was a need to develop a new model, which is called as, which was given by Bohr, right? And this is what we are going to study in the next class. So I hope you enjoyed this lecture and you gained enough knowledge, and I hope to see you again in the next class, and thank you for attending this lecture, right? I hope to see you in the next class as well. Thank you.